Now with Diffie Hellman, it's an asymmetric algorithm, so each user has their own private and public key. So I have my private and public key, you have your private and public key. In Diffie Hellman, we exchange public keys. So I have your public key and you have my public key. Now through the mathematics, I'm going to use my private key, which is just a number, and I'm going to use your public key, which is just a number, and I'm going to put it through this algorithm, and it's going to come up with a symmetric key. Now what you're going to do is you're going to take your private key, my public key, run it through the Diffie Hellman algorithm, and you're going to come up with the exact same symmetric key. So, you know, this is kind of freaky about how can you use different numbers and come up with the exact same value. But that's the excellence. I mean, that's why this math is elegant. And so what it allows us to do, you and I don't know each other, but we may need to communicate privately through encryption. So we'll just send public keys, and that's okay because they're public. Anybody can get them. We just exchange public keys, and with this algorithm we both have the same symmetric key. So that means you can use your symmetric key to encrypt a message sent to me and send it over, and I have the necessary symmetric key to decrypt the message, and vice versa. So, and this is the only algorithm that works this way. All the other asymmetric algorithms work the way that I just talked about, of encrypting that symmetric key and sending it over the message. Diffie Hellman is the only one that has one symmetric key that is created on two different systems. With the other asymmetric key, there's one symmetric key that encrypts the message that has to be encrypted and sent over to the receiver. Now, Diffie Hellman is based on calculating discrete logarithms in a finite field. We're certainly not going to go through that because I don't remember it from college. But it is something that you need to know. You'll need to know the type of mathematics that the different asymmetric algorithms use. So Diffie Hellman uses discrete logarithms in a finite field. Now, Diffie Hellman is also vulnerable to man-in-the-middle attacks. And the reason that it's vulnerable to this is if I send you my public key, how do you know it's my public key? What if it was somebody else's public key? You don't know because we don't have any type of pre-authentication. If we did some type of pre-authentication and I prove who I am, and then I send my public key over to you, then you'll know that's my public key. But that's not how Diffie Hellman works. We both exchange our public keys, and we don't know necessarily that it's really that person's public key. So that's how it's vulnerable to a man-in-the-middle attack. Now, does that mean that every time this algorithm is used, this flaw or this vulnerability is there? No. Because what happens is that whoever, like the developer, needs to understand how Diffie Hellman works and have something to do authentication before these public keys are transmitted, which is very common. It can happen with digital certificates that we'll talk about in PKI. So it's vulnerable to a man-in-the-middle attack, but it doesn't mean wherever it's used that protocol or that application is vulnerable. But if the developer does not understand how Diffie Hellman works and they don't put a compensating security mechanism in place, then it could be vulnerable to a man-in-the-middle attack. Now, Diffie Hellman is called, technically the right term for it is a key agreement protocol. A key agreement, because it's just exchanging public keys and creating that symmetric key. It doesn't do any, it doesn't itself do any data encryption, and it can't provide the service of creating digital signatures. It could just do key agreement protocol.